Good afternoon to everybody, and thank you for still being here. And also, I would like to thank very much the organizer of this beautiful event. And I hope that I will not disappoint too much Lucia and Matteo by presenting our joint results. So, the general topic of my talk will be the quantum enhancement of two photon processes by quantum entanglement. A topic which has raised, let's say, certain attention in the last 20 or 30 years, mainly because of its potential application to nonlinear microscopy, where actually the probability of two-photon interaction are so small that they impose high-intensity lasers, which may lead to damage or structural modification. So, nonlinear microscopy or even nonlinear spectroscopy. The main idea behind that is that entangled photons, pairs of entangled photons, typically generated by parametric down conversion, which are split from a single parent photon, behave as a single particle into photon interaction, leading thus to a huge enhancement of the interaction probability. And the formal support behind this idea is the presence of a linear dependence of the rate of two photon processes on the incident photon flux, in addition to the usual quadratic dependence of the two-step processes. The initial theory dates back to more than 50 years ago. So the initial work of model is 1968. While in the last, let's say, 20 years, a lot of experimental realization, experimental tests appeared. They mainly focused really in the low flux elimination regime, where this linear dependence is realized. And but actually, this is still a very, very debated topic, because initial experiment claimed up to 10 order of magnitude enhancement into the quantum entanglement. I don't know if you see here the numbers. This is classical to photon absorption, this is quantum to photon absorption. But actually, more recent measurement failed to produce this kind of result, so that skeptics argue that the linear procession should be lowered by at least 4 order of magnitude. But then there are also a series of other work, especially in the group of Riemann theoretical work, which suggests that at the low illumination fluxes where the linear regime occurs and where quantum enhancement is expected, the theory would suggest that the fluorescence signal should be actually undetectable at all. And in any case, they question whether this quantum enhanced fluorescence signal is really useful at this very low illumination fluxes. So how does our work is positioned inside this context? Well, I would like to exploit our know-how in the last, let's say, 30 years, especially at the University of Surrey, on generation, detection, and models of broadband parametric sources, which imply a very high-dimensional entangled space. So high-dimensional in space and time. And then use these states to explore the concrete possibility which are offered by entanglement with the enhancement of linear interaction and also linear imaging, when the entanglement is pushing the limit, involving then very narrow entanglement volume, so photons confined to really small space and time volume. Also, we would like to explore not to limit to isolated photon pair, but to explore the possibility of macroscopic or mesoscopic line field, which is obviously much more useful for applications. And also another point is that from a formal point of view, we develop models which are fully space and time. This not only is the only way to obtain quantitative predictions from the theory, but also it's important because it allows to model many different aspects which are not considered in the literature, like how does entanglement propagate in media, because you generate entanglement at the source, but then you have to deliver it inside the medium. And then eventually the optical sectioning capability of the entangled to photon absorption, which obviously in the linear regime is apparently lost. So what today I'm going to present you, is our work on the quantum enhancement of the second harmonic generation. Is also two-photon process, which bears a lot of similarity with the two-photon absorption. But we think that it provides a sort of much cleaner framework to study the quantum enhancement of two-photon processes, because it has not all the complication of the molecular structures. It's a parametric process, it's much simpler, and also experimentally it's much easier, much more efficient. So our main goal is comparing with the second harmonic generation from a classical coherent pulse, keeping fixed the intensity of the illumination and the total energy of the illumination. And we will also explore the transition from the spontaneous regime, where isolated pairs are down-converted and up-converted, to the stimulated regime where instead bunches of entangled photons are unconverted. The work is both theoretical and experimental. At the end, I will show you some results of the experiment, but since I'm a theoretician, I will be focused on the theory. There is also a poster disabling the experiment. So here is the scheme we considered. The entangled photon pair are generated in a forced nonlinear crystal. Then are reimaged by means of a by means of a 4F achromatic imaging system into second crystal, where a conversion takes place. So we assume the two crystals are identical, eventually they can be different for the length. We also assume that our imaging scheme is free from dispersion and doesn't make any significant angular cut, so that the significant portion of the frequency and the angle spectrum of the entangled pair can be transmitted. A specific feature of upconversion is that it's possible to discriminate, easily in experiment, between the quantum contribution and the non-quantum contribution. So contribution coming from entangled photon and contribution coming from a random recombination of non-entangled photons. Why that? Because, as Gary was mentioning, entangled photon, the phases of entangled photons sum up to a constant phase, which means that when they recombine in unconversion is also a coherent process, they form a coherent component, they form a coherent component of the second harmonic signal, which basically reproduces the original pump. So that, for example, in the far field, it forms a narrow peak which split over much broader background formed by the coherent component, and this can be easily selected by matrix, for example. So a few words about our model. First of all, how we model parameter down conversion. To do that, we use a recently developed model that we call quasi-stationary model, which assumes that there are two well-separated time scales, so a short scale associated to the decay of correlation with coherence, space and time, and a long scale associated with the slow revariant. Physically, it corresponds to small and correlated light spectrum inside a broader envelope. What I show you here is the Fourier spectrum, some numerical simulation, but the same thing has also been mentioned. So GER is approximated because it requires a long enough and large enough pump, but the limits are not very demanding and are also very close to typical experimental realization, especially the high gain regime. The good point of this model, let me advertise a little bit this, is that it can all quantities of interest can be calculated almost analytically or up to some integrals. No, aspetta che ci sono un pezzo. Aiuto. No, niente. And it can also predict many things, like, for example, the exponential shrinking of the down-converted field and increasing gain, so the profile, space and time. Or also the broadening of the spectral in correlation size, again, increasing gain, which are things maybe not so well. But the good thing for theoretician is that it is quasi-analytical, and it can account for past parametric generation. So, second element of theory, of course, we describe then the linear process. Don't worry about this function, they are all explicit functions of values parameters of the system. I just wanted to show you the general structure of our result. What I show you here is the second harmonic photon flux, the output phase of conversion crystal, as a function of the space-time coordinate, so psi the space-time coordinate. You can recognize here two different terms. W here is the Fourier coordinate, so transverse wave vector frequency. So here what you recognize is a coherent summation over probability amplitude, and actually this term represents in fact the coherent component corresponding to the upconversion of entangled photons. So what this quantity are? Well, this is the superposition or better integration over all the modes of the probability amplitude of generating the entangled pair crystal in conjugate modes times the probability amplitude of upconverted this in the other crystal. So the other term instead, you can immediately see it is a summation of probabilities, not probability amplitudes, not a coherent superposition. So the probability of independent of generating fantastic. I don't know. It's magic. That's magic. Yes. So probability of generating independent photons in two modes, and then the corresponding probability of converting them in the second crystal. And this represents the what I call the incoherent component. And you may notice here the factor of 2 in front of the incoherent component. And also to understand this term, we have to come back a little bit to the statistics of the squeezed vacuum state. And the state generated at the output of the first crystal is a highly multimode squeezed vacuum state, so highly multimode in space and time. Then the probability of detecting two photons, a photon pair, and the same space-time coordinate, so together as time, which is the relevant quantities of these photon processes, factorizes into three terms. Two terms correspond to the pairing of non-entangled photons, and it's just the normal classical term that you will have also in thermal statistics, which has affected the typical bunching of thermal statistics. While the other term is one that originates from pairing of entangled photons. And typically these three terms altogether are known what is designed what is known as extra bunching of the squeezed vacuum state. The quantity here, small n and PDC, is an important parameter, is hyperbolic sine square of the parametric gain, which tells you how are populated each node. So it's typically called the number of photons per node, tell you the average population of nodes. We recognize here typically quadratic dependence on this parameter, on the classical part, which is obvious. While in the contour part, you see here the origin of the linear behavior, so the linear and the quadratic behavior, but also you see that also in the quantum part there is a quadratic term in the number of photons per unit. And these originate from, let's say, stimulated processes in which entanglement is present not only between photons born from the same parent pump, but also between single and either photon born in different microscopic processes, but entangled because of stimulated processes. That is what is our classical benchmark. We want to compare with what happens in classical physics, but what we take as a benchmark. Well, our obvious benchmark is that we take a coherent pulse which has the same intensity distribution across session and time, same energy, so again, same repetition rate. And the rationale behind that is simply that we want to give them the same potential to damage the network, to damage the medium. But since this is, we assume a coherent and transport limited pulse, then then this angle frequency spectrum is much narrower than that of the quantum source. Hence, it can be very efficiently converted because it's very well matched. So, in a sense, we are giving all the advantages to the classical path and normal physics. Also, in the element pulse, you can assume no boundary equations so that a conversion of this pulse is described by a simple quadratic relation with density. Here is a constant quantity proportional to the effective nonlinearity and the length of the crystal. This kind, so this, what I'm saying, it appears rather obvious, this choice of benchmark, is not that standard in the literature, because usually people in the literature tend to assume a classical pulse, which has the same spectral properties as the quantum source, which we think is a bit unfair because obviously if you want to be able to claim the quantum advantage, we have to keep the classical benchmark all the advantage non-test. So it should be something standard. So in order to understand what this equation implies, we have integrated this equation using same-layer relation for Gaussian media and consider some example. This example, I am considering up conversion, down conversion, and down conversion to be identical video crystal, close to linear and degenerate phase matching. And what I show you here is probability amplitude of generating an entangled pair and probability amplitude of up conversion. Notice that the second crystal is 1 millimeter length, so shorter than the first one, which ensures that the response of the second video is basically flat within all the spectrum of the quantum source. So a high probability amplitude of up conversion. So what I show you here is the peak intensity of the second harmonic field is plotted as a function of photon number per mode, so at increasing gain. In the upper part of the intensity of the PDC beam. And this is 1 photon per mode. We have seen that 1 is the boundary between spontaneous and stimulated, so obviously the boundary because linear and quadratic behavior. Traditionally, it's expected to be also the boundary between any quantum advantage and classical, and you see obviously from the spot that this is not the case. The red line here is the classical pulse, the blue is entangled singular harmonic generation. In fact, so this in fact is not the case. This is just the same plot on a larger scale, and here I show you the ratio between entangled and classical reference intensities. So quantum advantage persists well beyond the 1 photon per mole boundary. So this is in a sense is the result which will be interesting in the CW case, while in the past case, obviously, is much more interesting to integrate the pulse to consider the photon number, the total photon number which has been generated, which I show you. So actually, if you consider the mean photon number per pulse, the result is even much sharper. So our entangled second harmonic generation appears more efficient than the classical counter, but it is a simulated regime. Let's say up to 20 photons per 15 to 80 photons per mole. Also note that at increasing gain, the quantum advantage tends to go at best to 1, which means that the performance of the entangled second harmonic tends to, at best, to be equal to the classical benchmark. Notice that here I'm showing you only the pure quantum contribution arising from entangled photons. But if you remember, there is also the incoherent contribution coming from non-entangled photons. So now, if I add this one, you see the upconversion of non-entangled photon in modes other than the quantum mode gives a reasonable contribution. And when I sum the two, so when I include the contribution both of entangled and non-entangled photon, the upconversion from the squeezed vacuum appears definitely more efficient than the classical benchmark at any gain we have at least. Notice anyway that at high gain, it is much below the value 3 that was expected from the extra bunching of the squeezed vacuum. Instead, if you want to achieve this limit, so limit 3, which is what is caused by the extra bunching, you have to consider a very short second harmonic crystal, in which case the second harmonic crystal has a huge bandwidth, which accepts all the possible processes also. So the non-entangled processes goes really in every mode. So in order to upconvert them efficiently, you need really short crystal. But with a short crystal, you can eventually reach the value 3 that was the maximum expected from the extra bunching in the statistic of the squeeze vacuum. So I want to show some now experimental results, some very short, this is poster result, if you're interested. Thomas and Livy are the person that mostly worked with this experiment that was set up in Glasgow University, now is being set up at Coventry University. The main challenge of this experiment is measuring the effect of second harmonic generation from the squeezed vacuum, ranging from the spontaneous up to the simulated regime, which obviously is not easy. And for this, it is on the experiment that two down conversion and up conversion crystal have the same length, which is 2 millimeters, which is a sort of suboptimal, but is a good compromise for ensuring the best efficiency. So it's not the efficiency, but the possibility of detecting also in the low gain. BBO as in the theory, all the rest of the setup is basically the same I described. In the theory, the optics is mostly reflective optic, so non-dispersive. The other challenge of the experiment was the generation of the classical pulse, which was derived obviously from the original laser. But the point is that the down-converted pulse shape changes a lot with gain, it shrinks a lot, both in time and in space, and then the classical pulse was generated by, needed to be tuned with the Crisp compressor on time and the spatial profiling to be also controlled. Some preliminary result about the characterization of down conversion. Measured down converted photons per pulse as a function of the quantum photons per pulse. Symbols are the experiment, the solid line is a theory, and well, this is the other plot, it's the same plot, just in linear space, so you can appreciate the exponential behavior. And the only thing that I wanted to remark is that theory does not contain basically any free parameters, so I have to come back to Gary talk. And the only adjustment that was done to theory was a small adjustment of the effective linearity, which is absolutely reasonable, also because there is some velocity mismatch, which is not considered by theory. So the good agreement between theory and experiment allowed us to measure the number of, to infer the number of photons per mole in the experiment from theories, and then this dashed line corresponds to the boundary between spontaneous and stimulated regime. So you see, the experiment ranges in those regimes. So this is the main result, comparison between second harmonic from entangled photons and second harmonic from the equivalent classical pulse. This result includes only the coherent contribution, which was the only one measured in this experiment, by using an iris in the far field of the second harmonic crystal. Well, again, solid equals an experiment, solid lines of the theory, and that also in this case, theory has a very good correspondence to experiment up to a small, so the conventional correction for nonlinearity plus 10% unavoidable losses. While I'm saying that, not because I want to say the theory is very good, but experiment is very good. Said that it's not very, doesn't happen very often that theory and experiment can be that well. But the point on which they both agree is with this kind of parameter is that the crossing between quantum and classical takes place at roughly 10 photons per mole, which clearly is much above the limit which was taken in the literature as being really the limit between quantum and classical, which is it was 1 photon per mole. So I don't think I have much time to. Anche perché mi funziona. I don't think I have much time to enter into all the kind of optimization that would be done for this result. Optimization which were done both in the theory and the experiment. One optimization which is not trivial is about the position of the second harmonic crystal with respect to the imaging plane in the fourth crystal. So you notice here a very so that by making just 300 micron error in this positioning, immediately your quantum advantage drop. And with 600 micron error, your quantum advantage basically appears only at a very low. So if you don't take care of this potential, you don't get this result. So like that, well, our beam is 1 millimeter beam, so there is no diffraction from the beam. The point is that you need to refocus very carefully the two photon probability. And these two photon probabilities this is a coherent process, as Daniel said before. It's very, very sensitive to propagation, which in a sense maybe can be used to find a gate, so to reconstruct the sectioning capability of the photon processes with entanglement. So other thing that needed to be optimized is the spatial temporal statistical source by a careful choice of the bandwidth that we use, which in our case was around 100 nanometers. So again, don't have now to into detail. The only thing that I want to stress is that only in this case, that also in this case, there is an important phase effect, which is due to the fact that bifocals, which in principle are very close to time at the source, they broaden even propagating the source because of dispersion, because it's bifocal amplitude behave coherently, while random processes not so far from the same problem. So this poses limitation on the bandwidth that you can convert with having a functional advantage. But also we are exploring the possibility of making some precompensation dispersion. So let me conclude. So we have demonstrated both in theory and experiment, which can take very well. The possibility of enhancement of the process by one entanglement well beyond the 1 photon per mode boundary, which obviously is crucial for application and opens the way with more confidence to application. This requires a careful optimization, what can be done. Also, I have to undercover result demystify a bit the role of entanglement, because at I gain the poor quantum contribution at most equal the classical counterpart. But when you consider also the contribution of incoherent processes, which are always there, this establish a solid superiority of the second harmonic generation from the squeeze vacuum with the rest of the classical quantum. So with this, let me thank you for your attention.
Alessandra, for the interview, we have already questions.
So very nice to have a question because probably I missed something because I don't exactly understand because you compare the result of SAG from a classical field, let's say a coherent state or a state, and a coherent state and a squeeze vacuum state. Right?
Yes.
Okay, so I can understand that the squeeze vacuum state may be converted, as you show, for a small number of photon per mode, much better than a coherent state. Okay.
No,
so I can understand that a squeeze vacuum state may be converted with a better efficiency than a coherent state, okay, in SAG, when, for example, as you showed here, the number per photon per mode is small. Okay.
No, the number I say I'm the
yeah, but I don't understand the rule in telling it in the sense that I need to compare, for example, squeeze vacuum state with spin number 1 with squeeze vacuum state with spin number 10, and then I would see the conversion efficiency, and in that case I would say.
What do you call Schmidt number? Sorry,
of the measured entanglement. Yes, the number of Schmidt modes, making a Schmidt because if I have a squeeze state, I mean, of
but
course.
the number of photons per mode then I mean, this is basically the Schmidt number of entanglement. The single mode squeeze vacuum.
So that is the Schmidt number.
I don't remember there is a factor of 2 with a big or something like that. Basically, if you calculate the Schmidt number for the single mode squeeze vacuum state, well, this is it.
This is not, this single mode squeeze vacuum.
Yes.
The Schmidt number is 1.
Well,
It's not
that's why I asked you what is the Schmidt number, because The Schmidt number can be defined as the number of nodes, that is one, obviously, but also the inverse of the cubic of the state. It's not one,
Yes.
with this measurement entanglement. Sorry, the single most squeeze value is entanglement. Really. But obviously, you have to divide the two integral components to measure that, but it is entanglement. It's not that entanglement is only properties of multi-node. You have to at least to have a bipartition, but then if you put the squeeze value on a discrete, you have to.
So you
Well, entanglement model.
So the point is, how you measure the entanglement in your squeeze back?
We do not measure, we assume it's there in the sense that in the number of photons per mole, you, in principle, how much squeezing you have on each single model. Then we have like 30,000 modes. It is highly like stable. We don't measure it in the sense that it's something which is, it was object of many past measurements. So once it is generated, also because actually I'm calling it entanglement. Okay, it's entanglement. But the enhancement actually comes from the fact that you are generating photons in pair and then originally basically vacuum. So I don't think we need to measure how much entanglement we have, but of course, it would be interesting. Also, at the same time,
how much was not a totally missed square. So
but I did explain.
Okay, yeah, just a bit late, so I suggest we leave out a note.